right. Questions? PA5, PA4 stuff. All right, well, we're going to keep going with threads. Is the synchronized method built in, or do we need to import? It's built in. It's a keyword in Java. So let's let's talk about synchronizing. So we looked at the let's see. I got PA5, so two games can connect, but I'm confused how to send information back and forth. Okay. So once you're connected, right, you can open a print writer by using socket.get output stream, and you can open a scanner with socket get input stream. So you have client and server, and you have the ability to write something in a print writer here, read it from a scanner over there, and vice versa. And so the main thing you're going to share is mouse clicks. And so in your mouse click listener, you pop into a listener which is passed in mouse click event, and you can use get x and get y to get xy coordinates. So just like you were doing in PA4, but the first thing you have to do that's different is see, is it your turn? Because in PA4, anytime the mouse is clicked, we assume whose ever turn it is the person who clicked the mouse, and we go ahead and we continue and process the XY. But in this case, you need to keep track. If you're the server, it's your turn to begin with. If you're the client, it's not your turn. And every time that a turn is taken, you switch your flag. So first thing you have to do in your mouse click listener that's different from PA4 is make sure it's your turn. And if it's not, you can just throw up a message saying, wait until it's your turn. The other player is still deciding, whatever. But if it is your turn, you go ahead and you do all the stuff that you normally do when you respond to a mouse click, but you also send to socket the XY coordinates of the mouse click. And send to socket can be a method inside your netThread, so call netThread dot send to socket. And the goal of that method is to send a message. If you're on the client, send it through your print writer so that the server will pick it up on their scanner. And what's the message look like? Well, it could be something like, the letter C space, the X coordinate space, and the Y coordinate. That's a one-line message that you have to split up when you receive it from the scanner and say, oh, there was a mouse click, it was at XY. And now, on the side that didn't do the click, you go ahead and you call your click code that you would use in PA4 when the mouse was clicked, right? But since it's the other player's turn, right, their initial will show up if it completes a box, and so on and so forth. Tell me what you mean by atomize. You mean what we were talking about yesterday? No, probably not. The only time you might get into trouble is if I get a message saying the other side clicked, and I call my mouse click code, and at the exact same moment, the person sitting here on this side clicks their mouse when they're not supposed to. And it's possible that, I could have two threads running my mouse click code at the same time. And depending on what you do in there, yeah, maybe you could get into some data corruption. Do we need to call the mouse click listener from the netThread? You're going to call the code that you run in your mouse listener, but you're not going to actually call the mouse click listener. So look at PA4. So in PA4, you had a mouse click listener set up by Window Builder probably. You did a bunch of stuff in there and then you said return. Okay, PA5, you're going to want to change that. So on a mouse click, get your XY coordinates, but change do stuff to a method. Right? Don't just put your code inside the mouse click listener. Move that into a separate method, and then in your netThread, receive your XY from the socket, and then call do stuff with XY. So the effect is when you get an XY pair from the socket, you're doing the same things that you did inside your mouse click listener in PA4. But don't try to actually call the listener itself, because then you're interfering with swing. But all the stuff that you would do in response to a mouse click, do that in response to receiving an XY from the socket. And just, instead of writing the code here and writing the code here, throw it all inside a method called do stuff and just call it from both places. Exactly. You call do stuff up here and you call do stuff from the netThread. That's how I would suggest doing it. And if you put do stuff, inside the jpanel method, you're going to need to have some way for the netThread to have access to that method. So this is what we were seeing yesterday when we constructed this. We passed it this, which was our identity. So if the panel constructs the netThread, which is probably the best place to do it, in the constructor just pass this so that the netThread knows the identity of the jpanel, and then it can use the jpanel.dostuff method. Start the netThread from, yes, sort of. Started when the person either clicks the start button on the server side or clicks the connect button on the client side. And those buttons, were probably part of the JFrame or a JPanel. And so that's where you want to go ahead and start the netThread. So construct it and call the start method. So yeah, it is from a mouse listener, but not the mouse click listener. Just from the thing that's waiting for a button to get clicked. You're calling do stuff twice because there's two situations. So what does do stuff do? Let's make it a little more specific. Do stuff, and don't call it do stuff, but find the row column corresponding to XY. Find edge of box that XY is closest to. Is it already true? If yes, that's an illegal move. If no, set it to be true. Box completed. If yes, set owner. If no, change whose turn it is. Something like that, right? This is what do stuff is. Well, there's two situations in which all of these things need to happen. The first is, it's your turn, you click the mouse. Right, I went up to the edge of some box, I clicked the mouse, I need to find out what box I'm in, see what edge I clicked next to, make sure that edge is not already set, and if it is, set it to be true, see if a box was completed. The other situation in which all of this is going to happen is when it's the other player's turn and they click the mouse. And when it's the other player's turn and they click a mouse, their netThread is going to send a message to me, right, which is going to say, hey, the other person just clicked at this XY coordinate. And what I need to do on my board is take that XY coordinate, turn it into a row column, see which box that is, see which edge we were closest to, set it to be true, see if a box was completed, and so on and so forth. In PA4, right, the only time that this happened is when you click the mouse. But, you know, one time it's me clicking the mouse, the next time it's my friend clicking the mouse. But it's the same code. But in PA5, those clicks happen on different machines. So when I click the mouse, it's going to, you know, be my mouse listener that gets called, and I could have this code inside there. But when my friend on their machine clicks the mouse, there's going to be a message sent, and my netThread, which is listening to a scanner, is going to say, hey, somebody just clicked the mouse, and it's going to have to do all of this stuff, right? So we're doing this in two different places now instead of just in one place. Cool. So this was the code that we were playing with yesterday, and we saw how to make it work at the end. So just going back a step, right? This was a thread. It would increment a tally 10,000 times. And when we run it, we get these weird results where sometimes it does the right thing, but a lot of times it doesn't. And so we talked about using the synchronized keyword. So let me retag this. So we talked about how we could use the synchronized keyword. Oops. To lock on an object. And we can put any object in here that we want. And we created a lock object, but you know, we could also just lock on the parent, because each thread has the same parent object. So we could just use parent as the thing we lock on. And that'll bring us back to our preferred mode. Yeah, we could use a triangle. Definitely. Or the stick game object. Nobody's implemented a stick game class as far as I can tell in here. You could make like a class called stick that you know, you construct it and it plays the stick game. And then we could lock on that. All right. There's another way we can synchronize. So this is very sort of tactical. Um, this is saying, you know, everything within this block is synchronized, and so this will only happen once. And it's a single statement, so, you know, in between this statement, which is when we're incrementing I and comparing it to 10,000, that's when other processes could kick in and start executing this. Um, oh no, someone forgot the stick game. Oh, that would be cool. Nice. So there's another way to synchronize, and it's in some ways a little easier, but it's potentially a little sloppier, and that's you can synchronize an entire method. Um, so I could take this, and instead of doing this, I could say just increment the tally. So I'm just going to move my increment, my plus plus tally into a method here, and this is kind of silly to do, but you know, you might have some big chunk of code that that's doing something that might be shared. And this should be parent.tally. Right. So this is misbehaving because, you know, that method can be called simultaneously from different threads. But rather than put the synchronized keyword, I can say this entire method is synchronized. So I can say public synchronized void inc tally. And now we've, ooh, or not. Ooh. Well, that's a fail. Maybe that's only within one thread? Huh, I gotta check on that. Anyway, I'm not doing that right, but there's a way to do that. I don't think this makes a difference. Oh, that's disturbing. So I don't think you have to specify an object when you synchronize a method. But I could be off on that. All right, we'll come back to that tomorrow because I'm spacing on how to make this work. But there is a way to synchronize at the method level, which you might want to do for your mouse click listener, but probably not a problem, right? Like I say, the only time I think you can get into trouble with the mouse click listener is if you happen to click the mouse when it's not your turn at the same moment that you've gotten the packet from the other side that's also trying to call the same code. And so, for example, you might have two things trying to update the score, and they could interfere with the score or something. But you can always use the synchronized block to set that up. All right, so let me make a note. Figure out how to synchronize methods. And that's a little weird because I tried that yesterday and it worked. So on the topic of synchronizing, right? We've seen that something as simple as, you know, incrementing an integer is not what we would call thread safe, right? It's thread unsafe. If we do this one statement from two or more threads, we can get unexpected results. So there's this notion of thread safety, and most of the Java documentation talks about thread safety, which is basically the notion of is it safe to do something from multiple threads without managing synchronization on your own. And so, for example, if you look at the linked list documentation, it says this implementation is not synchronized. If multiple threads access a linked list concurrently, at least one of the threads modifies the list structurally. It must be synchronized externally. So this is typically accomplished by synchronizing on some object that encapsulates the list. If no such object exists, the list should be wrapped using, etc., etc. So we touched on this briefly when we looked at some of these things like linked lists before, but, you know, suppose you have a list which has, you know, some data in it. And suppose you have two threads that are both referring to the same object. And suppose this list is trying to print the contents, this thread is trying to print the contents of the list, while this thread is trying to delete something from the list. So let's say this is trying to delete the number 4, and at the same moment another thread is trying to just print the contents, so it's calling the toString method. Well, you know, this is running some code. We don't know what that code is, but it's doing something like what we did in 222. It's got, you know, maybe a temporary variable, which points to that too, and prints out its data value, and then sets temp equal to temp next. So now it's pointing to this. And maybe at that moment, you know, this thread deletes that from the list and changes 2 to point to the 10. And now, you know, this temporary is pointing to this 4, and maybe 4 has been changed. Maybe something else is using that, and this is pointing somewhere else. And this thing, which is trying to print out the contents of a list, is now off on a wild goose chase. And so the documentation will tell you when certain things, methods, and such in different classes take care of this for you or don't take care of it for you. And by and large, these things don't take care of it for you. So most of this stuff is not thread safe. And that includes swing. So a lot of stuff that we do in swing is not synchronized for us. And that sort of makes sense because synchronizing is kind of heavy, right? It disrupts the whole idea of threading. When we add synchronization to a chunk of code, we're saying only one thread can run this code at a time. And we don't really want to make that a default, right? Because we can always add synchronizing, but it's really hard to take it away. So the kind of go-to behavior is everything can run at the same time, everything can do anything it wants simultaneously, no worries about what else is going on. And then it's up to the programmer, that's you, to add controls to prevent simultaneous execution. Alright, so that's thread safety, and like I say, most things that you look at in the Java documentation will talk about that. And when you're writing code, right, if it's code that you're going to use potentially in a threaded situation, you want to think about, you know, is this thread safe? and either, you know, do something to make it thread safe or put a note in your comments that you know, it needs to be synchronized. And so again, you know, PA5, you have potentially two things that will be updating your board memory, right? So mouse clicks and your netThread. And if both of those run at the same time, can you get into trouble? Possibly, depending on how you're storing your information. Now, if you're just going through and you're setting booleans, then you're probably okay. But I'm sort of envisioning if you've got something like this, you should be okay because only one click is allowed at a time. But for example, if we were at a different situation where there could be two legal moves, and maybe, you know, one click comes in right here and another click comes in right here, and if both versions of do stuff were running, right, and you were just keeping track of score statically, you might see that this completes a box and add 1 to your score. And at the same time, this other thread might see this line being drawn, not know that this boolean has been set true, and say, oh, you just completed a box, and add another 1 to the score, and your score might go up by 2, for example. So not going to be a problem in PA5, but, you know, an example of where that can come into play. All right, so there are a few other things in threads that we might like to play with. So one of these is join. So join is a way to basically wait for a thread to finish or to die. And let's go back to the code we had earlier. So I'll leave this with broken code. And it works sometimes and it breaks sometimes. And the reason I was printing out the tally from each thread as it exited was because my main program exits before these threads finish. Right? So if we look at main, it constructs the go object, it exits right away. If we look at go, the go method actually exits right away, and then main exits. Let's see. This method seems a little morbid. Yeah, so well, that's true. It is circular. Yeah, so I mean Unix has zombies and orphaned processes and parents and children and killing and all this kind of stuff. So yeah. Yeah. It is interesting that that's the terminology that comes to mind when you're developing this stuff. Maybe we could rewrite that terminology. So I start these threads, right? This go method exits right away, which is why, you know, trying to print the values of those tallies right here wouldn't do any good. So if I tried to do something like this, main system exiting now, And let's print out the final tally. Right, and so my final tally there was, you know, significantly smaller because the main program exits so quickly. I don't know how low I can get. So, I'm reading chat. Yeah. So here's what we can do. We're going to start threads 1 and threads 2, and they're going to run in the background, but we can say wait for each thread to finish. So we can just join those threads. So join is a method which is waiting for the job to die, the thread to die. And this can throw an exception. It can throw an exception if something interrupts the thread. I'm not going to get into interrupts, but I won't be able to compile this because it'll want me to catch that exception. So I'm just going to throw these joins into a try-catch block. And I'm not even going to worry about what kind of error might come up there, because I'm not expecting an error. So now if I run this, it tells me final program tally equals, and it shows me what the actual tally was. And the program doesn't exit until both threads have exited. And that's totally consistent and reliable. And I left the unsynchronized tallying in there just to make the output more interesting. So this is how we can know when our threads are done, so we can call the join method. So typically, you know, you want your threads to run in parallel, but there may be some things that you want to have wait until your threads are done, and then go on and do something else. So that's what join will help. And there's other versions of join, so we can join and we can say how long we want to wait. So we can join with a number of milliseconds, and then if that much time passes, we'll come out of that method call and continue. All right, I'm hesitant to go over this next thing. So I'm going to make an appeal up front. Please don't add sleeps to PA5. Okay? It's a nice user experience in general to be able to introduce delays sometimes in gameplay. That's not what I want when I'm grading, you know, 30 or 40 of these things over the weekend. So please don't introduce delays in PA5. Okay? Unless you know, have a special switch called, you know, dash relax or something. But by default, I don't want to have to wait, you know, like take a moment and breathe before beginning or something like that. So, because I don't breathe when I grade. But let's talk about how we could introduce delays. So threads come with a method called sleep, and sleep is a static, so we don't actually need a thread to execute a sleep. It's a static method, so we can say uppercase thread dot sleep and go from there. So let's see. All right, so let's make yeah, there you go. So let's write a method called wait that'll just hang out for a second, and we'll do a slow countdown here. So thread.sleep takes an argument in terms of milliseconds. So we'll just thread.sleep for 1,000 milliseconds, and that should be a 1 second delay. It can throw an exception, it can get interrupted, so we need to, oh, I gotta do statics. Oh well. Alright, I won't get fancy. Let's just do this. Right, so that sleep can get interrupted. It's a potential exception, so this has to go in a try-catch block also. And I'm not going to worry about what the exception is. So if we run that, you know, we've got a 1 second delay. So that can be useful. I should have stopped at 1, not 0, right? So that's in your bag of tricks, and you can sleep for milliseconds. You can also sleep for milliseconds and nanoseconds if you want really precise timing. Whether that's meaningful on a JVM, I don't know, but theoretically. So you can go up to 1,000,000 nanoseconds. It's exciting. There we go. All right. Is there an OS where Java code runs native? I think so. Yeah, I'm pretty sure there's Java machines. Not Android though. So Android really runs on top of ARMS usually, and there's a JVM of sorts. But I'm sure somebody has built Java machines, because people used to build Lisp machines. So Java processor implementation of the JVM in hardware. So Pico Java by Sun, which is old. There's some ARM-based versions. This might be a good wormhole to go down. Or not. Try Googling that though, I'll bet it's an interesting read. You have Sun Systems at work, cool. Yeah, Sun was an awesome company, man. That was good stuff, and you know, that's where Java came from. And they used to make these awesome rings that ran Java. That was an old marketing thing they did. All right, yeah, Sparks. Those were awesome. All right, so let's start talking about the dining philosophers. That would be cool. So Dining Philosophers was a thought exercise, and this is credited to Dr. Dijkstra from Dijkstra's algorithm, right? Who was looking at the question of concurrency. And so, you know, back in 60s, 70s, you didn't have PCs. You had basically a mainframe sitting in a room, and there was a printer connected to it. There was a card reader. There was a paper tape punch, a magnetic tape reader. All these peripherals attached to this one CPU. And suppose you have multiple jobs running. So machines used to run one job at a time. Start your job, it runs, finishes, the next job comes in. As machines became time-sharing systems, you would have multiple jobs running. This job would run for a little bit, and then this would get a little bit of time, and they would sort of take turns at the CPU. And if you had 5 jobs, they'd alternate in some schedule. And the question comes up, you know, what if 2 of these jobs are trying to print something, right? You would have a problem because, you know, this job would send a few characters of its print job, and then this would send a few characters of its print job, and this poor printer, it, you know, gets a character, it prints it out, and you would get, you know, a mishmash of the printed information from the 2 jobs, and it's meaningless output. So as soon as you start having multiple processes, what we're calling threads in Java, you need to start worrying about resource sharing and resource allocation. So how do you stop the printer from printing 2 jobs at once? Well, you do some kind of locking, some sort of synchronization. So for example, you could, you know, have a flag, and when a job is going to start printing, first it checks to see if the printer is in use. And if it is, that job waits. If the printer is not in use, it puts up the flag and says, hey, I'm using the printer, and then it goes ahead and prints. And that works great most of the time, but what we were seeing yesterday was that, you know, it's possible that 2 jobs check for the printer being in use, both see that it's free, both put a flag up saying, hey, printer's in use, and they start printing. And you've got a problem. And so Dijkstra came up with this fictitious thought exercise as a way to analyze these kinds of situations. So here's the setup for the Dining Philosophers. So typically you have 5 philosophers sitting at a table, and you have a bowl of noodles in the middle, and you have an infinite supply of noodles, so it's like a physics problem, right? Unlimited supply. And we typically do this with 5 chopsticks. And so here's 5 philosophers. And there's a single chopstick in between each pair of philosophers. So I'll draw some noodles in here. Those look good. We can have steam coming off them because they're hot. All right. The ground rules are, in order to eat, you have to have a pair of chopsticks. And if you have a pair of chopsticks, you eat for a certain amount of time, and then you put the chopsticks down and you talk. And you're not allowed to talk while you're eating, you're not allowed to eat while you're talking. And a successful dinner party of these philosophers means that, you know, everybody gets to eat, nobody starves to death, everybody gets to talk, and so on and so forth. Yeah. All right, so the question is, how do you program these philosophers to act in such a way that everybody gets to eat, everybody gets to talk, right? Nobody starves, and so on and so forth. So it's a resource sharing problem. And there's, you know, some kind of first order approaches you might take. Well, you would hope everyone would get to eat. So yeah, what are some approaches we could use? How could we you know, what would be the instructions you would give to each philosopher so that everybody gets to eat, and so on? So round robin, so spell that out. Give me a step-by-step algorithm for each philosopher. Algorithm they're each going to follow. Time limit for having chopsticks. Okay, so how do they get their chopsticks? Because initially they're sitting here and the chopsticks are sitting next to them. So you have to pick up your chopsticks. How do we tell them to pick up their chopsticks? Fight to the death. Excellent. I want to go to your dinner parties. So they need both. So I'll start it off here. Let the philosopher on top be philosopher 1, followed by 2, 3. So these are identical philosophers. We're going to give them each, their copy of the sheet of instructions for their algorithm. But this is one approach. Is if we were to number them, we can have certain algorithms. But if all of them are the same, we could do something like look for a stick on the left, if available, pick up. Otherwise, wait, and then look for the stick on the left again. If you succeed in picking up the stick on the left, look for stick on the right. If available, pick up. Else wait, and go back and look for the stick on the right again. Now you've got both sticks. You can say eat for 1 minute. Put down stick on left. Put down the stick on the right. Wait 1 minute, and then go back up to the top. So yeah, we'll put a time limit on how long they can eat. We could make it random. We could make it more than a minute, but we certainly don't want somebody to eat forever, because if this philosopher is eating, they've got both of these chopsticks. Neither of these philosophers can eat. So we're gonna have to have some kind of time limit. And this is not a bad first attempt, but this is not going to work in some cases. So for example, suppose they all sit down and they all start executing this algorithm at the same time. So the first step is look for the stick on the left. So each philosopher looks to their left and they see a chopstick. And so each one picks it up. So this stick goes to this philosopher. This one goes here. This one goes here, this one goes here, and this one goes here. And now they all say, look for a stick on the right. And each philosopher looks to the right, and there's no stick available. The stick has been picked up. And it says if it's available, pick up. Otherwise, wait, go back and look for a stick on the right. Well, we've got starvation. Because nobody is ever going to put down their stick until they finish getting the stick on the right. They eat for a while and then they put down their sticks. And if you attempt to pick up a stick at the same time, wait a random amount, but how do we know that that random amount is going to be random? Right, if we pick two random numbers, they could end up being the same number at the same time. So this starts to expose some possibilities. Deadlock, livelock, starvation. These are all operating system concepts when we deal with shared resources and processes. Likelihood they all get the same random number. Well, for the humble philosophers eating noodles, probably not a big deal, right? But for a Google server, serving up X terabytes per minute of data, those small random chances will generally occur at some point, and they can be disastrous when they do. So we're kind of looking at worst case, super pessimistic scenarios here. But again, it's a thought exercise, basically. So we'll play more with this later, and and um, and see how some of these things like deadlock and livelock come into play. Cliffhanger. Okay, so tomorrow's Thursday. Let's do an open lab tomorrow. So no new lecture. We'll do open lab. Please come in and work on PA5. If you've got questions about it, let's go ahead and get those ironed out. All right, cool. Have a good one. Sun's out. Enjoy the day. I will see you next time.